Today on Macaulay Math, we're doing linear approximations with differentials. Intro. Okay, good day. I'm Professor Macaulay. This is Math 200, Calculus 1, Lesson 20 on differentials, linearization, and linear approximation. Our goals for today: we're going to understand the concept of tangent line approximation. We're going to compare the value of the differential dy with the actual change in y and delta y. We're going to estimate propagated error with a differential, and then we're going to find the differential of a function using a differential formula. This lesson uses the tangent line to approximate the value of a function at a given value of the independent variable. Using this method can be advantageous when the function in question is either unknown or if it's difficult to compute. It must be noted that the linear approximation is only useful when the value of the function being calculated is relatively close to the point of tangency. To see why, let's look at a demonstration. Let's suppose that we have a function that we either do not know or cannot compute, drawn here in yellow. But we do know the rate of change of the function at a point x on the function, shown here in pink. If we know the rate of change, which is a slope, and we are given a point, then we can write the equation of a tangent line, shown here in green. Now the green tangent line is an approximation for the yellow function. If we move delta x units to the right of the function, we can see that for small values of delta x, the blue point on the tangent line is a reasonably good approximation for the red point on the actual function. The further away from the original point, the worse the approximation is going to become. Tangent line approximation. If a function f is differentiable at c, then the equation for the tangent line at the point cf of c is given as y is equal to f prime of c times the quantity x minus c plus f of c. Now this is just the point slope form of a line where this f prime of c stands in for the slope. This is known as the tangent line approximation. It is also known as linear approximation, or the linearization of a function f at c. By keeping the values of x sufficiently close to c, reasonable approximations of f of x can be made. Alright, so let's take a look at something like that. Let's have an example here. Given the function f of x is equal to x squared minus 4x and the point 5, find the equation of a tangent line. Now, normally f of x is going to be difficult to compute, or you might not compute it at all, but just for the sake of this course, we're going to give you a function that you can compute. So we want to find the equation of the tangent line. So part A, the first thing we need to do is find the slope of the tangent line. So we need to do that by deriving f, and we'll get just 2x minus 4. And so we can calculate f of 5, and it's this 5 right here, the value for x, that's 5. So 2 times 5 minus 4, 2 times 5 is 10, minus 4 is 6. All right, so they give us that y is going to be equal to f prime of c times x minus c plus f of c. All right, so we already have calculated f prime of c. It's 6. And then c is going to be 5, so we're going to go x minus 5. And then f of c is given to us. F of c is going to also be 5. And so when I distribute, I'll have 6x minus 30, and then plus 5 gives me a tangent line of 6x minus 25. There is my equation of the tangent line. Part B says, use the tangent line to approximate f of 5.01. So our approximation is just plugging that 5.01 into this function. So this is our approximation because, again, it's a tangent line approximation. Y is equal to 6 times 5.01 minus 25. And so that approximation if you put it in your calculator, comes out to be 5.06. And then part C says calculate f of 5.01. And so we're going to actually plug that in for f. And that'll give us 5.01 quantity squared minus 4 times 5.01. Now, where did I get that? I get that from the original function right here. And when I calculate that, I end up with 5.0601. All right. So we could say in part D, compare the results of C and D at x equals 5.01. The tangent line is a good approximation because it is only off by 0. Let's see here, 1, 2, 3, 1. All right, the derivative as a differential. So the second part of this lesson is talking about differentials, and we're going to use that as we move into the last unit of this particular course. And we've seen this notation already. This notation tells us to derive y with respect to x. And if we do that, we'll get dy over dx is going to equal f prime of x. Now, this and this, we've said it before, but this is the differential of y, and this is the differential of x. Now, you see me use this notation a lot. And the reason that I do it is because I want you to be comfortable with the fact that this thing here is a fraction made up of differentials. And so just like in any other fraction, I can multiply both sides by the denominator. And so I can say that dy is equal to f prime of x times the differential of x. And so this thing here is the derivative as a differential. So just to formally define that, let y equals f of x represent a function that is differentiable on an open interval containing x. The differential of x, denoted by dx, is any non-zero real number. The differential of y, denoted by dy, is dy equal to f prime of x times dx. Since the differential of x, dx, and the differential of y is dy, an approximation of the rate and change of y, dy, can be made this way. I can use this differential formula, and I can substitute a change in y, dy, or I can say that the change in y is approximately equal to this differential expression, f prime of x dx. Calculating error with differentials. Possible or propagated error versus relative error or percent error. The propagated error is going to be the dy at a given value. The relative error is going to be the propagated error divided by the value of y at that point. Some differential formulas. So these are just the differential forms of the derivatives. You'll notice if we go back to this definition, we said the derivative as a differential, dy. We are going to have a form of that for each of the rules that we've already seen. So the constant multiple rule, the derivative, the differential of a constant times some expression is just going to be the constant times the differential of that expression. The differential of the sum or difference of two expressions is just going to be the sum or difference of the differential of those two expressions. The product rule, if you take the differential of a product of two expressions, then it's going to be the first expression left alone times the differential of the second expression plus the second expression left alone times the differential of the first. And then the quotient rule, remember our Hody-hi minus Heidi-ho all over ho-ho, the same thing. The differential of a quotient of two expressions is the bottom expression left alone times the differential of the top function minus the top expression left alone times the differential of the bottom expression all over the bottom expression squared. So we're going to find dy and the differential of y. All right, so our x value is 2, so we want to calculate delta y. Delta y is just going to be the value of y at the indicated additional. So it starts at 2 and we're going 0.01. So it's going to be y of 2.01 and we're going to subtract just y of 2. And that's how we're going to calculate our delta y. And so if you put it in a calculator, and I'm trying to keep it short, so if you need to pause and you want to put it in a calculator, but you can trust me on this. Y of 2.01 ends up being negative 10.322, and y of 2 ends up being just negative 10. And so when you subtract those, you get negative 0.322. Now, if we want to find the differential of y, we got to derive y with respect to x first. And so we'll get dy over dx is equal to, well, the 6 becomes 0 because it's a constant. We bring down the 4, so we got negative 4x to the third. And then I want to rewrite that as a differential. So dy is going to equal negative 4 times x to the third times dx. And so we're comparing dy and delta y. And so to calculate that, what we're going to do is we're going to plug in those values again. So 4, and then we'll have, it'll be 2 to the third, and then we'll multiply by our differential, which is 0.01. And when you put that in your calculator, it ends up being negative 0.32. And you can see again, we're only off when it's pretty close. We're only off by a very small amount. We're only off by 2 1/1000ths, which isn't too bad. Now, find the differential dy of the given function. So here we're going to rewrite this. Remember, this is a quotient. So we'll say that dy is going to equal u dv minus v du all over u squared. And so we can say that dy is going to equal, the u function will be x squared plus 1. The dv function, so here we have a chain, so it's got to be 2 leaving the secant alone, and then we're going to derive, or going to multiply by the derivative of the secant function. Now the derivative of secant is tangent secant. And then we're going to subtract the bottom function, and then we're going to subtract the top function left alone times the derivative of the bottom function, which will be 2x all over x squared plus 1. Now, the only simplification that I really see here, since this is a term and this is a term, is to simplify that. So I'll get dy is equal to x squared plus 1 times 2 secant squared x tangent x, and then it's minus 2x secant squared x, and then that'll be all over x squared plus 1 quantity squared. Now I know that that looks ugly, but it is usable in that form, and if we knew what x was, we could plug in and calculate dy. Last example. The measurements of the base and altitude of a triangle are found to be 36 and 50 centimeters respectively. The possible error in each measurement is 0.25 centimeters. Use differentials to approximate the possible propagated error in computing the area of the triangle. So for part A, we know that the area of a triangle is equal to 1/2 the base times the height. We also know that the possible error in each is going to be 0.25. So our delta H equal to our delta base equal to our DH equal to our DB is all going to be 0.25. And so I find my differential here using the product rule. And so I'll have dA is equal to 1/2. I leave the first one alone, so it'll be B times the differential of H, so DH, plus I leave the second one alone, H times differential of B, which is dB. And so now I'm going to plug in. So now I can plug in dA is equal to 1/2 times the quantity. B is 36, DH is 0.25, H is 50, dB is 0.25. And when I calculate that, I end up with plus or minus 10.75 centimeters squared. This is my possible propagated error. My percent error. Percent error is just going to be dA over the actual area. Now dA I get from here, so it's just going to be plus or minus 10.75. And then my actual area. Well, my actual area, I use the area equation. A equal to 1/2 the base 36 times the height 50. And when you make that calculation, you end up with 900 centimeters squared. And so we're going to take that 900, and when you do that division, you end up with 0.01194. Now that is not in percent. We have to multiply that by 100%. So we'll put the 100 here. We'll multiply 100 there, and we can say that this is plus or minus 1.194% error. That's what we have. All right there, folks. That one wasn't as bad as the past two, so we'll take a gift when we can get one. And a Star Wars fun fact of the day. Saw Gerrera, played by Forrest Whitaker, is not the first character in a Star Wars to appear as an animated character first and then is live action. So here's his younger version from the Clone Wars, and here is his older version from Rogue One. Boba Fett first appeared as an animated short inside Star Wars The Holiday Special, and then he became the famous character that he is. Well, that's all I got for today, folks. Have a good day. Bye.